Okay, so maybe I'll just say the kind of most important, the main input into proving this theorem is a corollary of this Kuznetsov trace formula due to Desiree and Ivanic. So main input so is a theorem of so maybe I'll just state it in a very simple form, and then I'll kind of say what a more general version is that'll be the one that's actually used. But so I'm going to let C, M, and N are going to be 3 parameters. And then I'm going to let G, M, and C be a function, a non-oscillatory supported on a product of these 3 intervals. So what did I start with? M. Okay. Then I sum over C and a sum over M and a sum over N. Okay, and then A sub M and B sub N are any sequences of complex numbers, of course. Bn, and then here I've got S, M plus or minus N, C. Okay, then I have the following estimate. I have C to the 1 plus epsilon root Mn, and then the L2 norms of A and B. So remember here that this is we've been using the classical normalization of this Kloosterman sum. So this is actually about size C to the 1/2 if I take the Weil bound. So this is kind of saying that I save a full power of C to the 1/2 when I go in average over over many different moduli. Okay, so if you compare this to what Philippe wrote down in his lecture, and if you maybe take the situation where M and N are both about C to the 1/2, which is sort of the hard range, here you see once you average over C, you save a full half power of C in that point. So often when we're doing analytic number theory, we have sums inside sums inside sums inside sums, so often you can get more cancellation rather than just taking absolute value all the way in. Okay, so what actually goes into the proof of this theorem is something slightly more general, which I alluded to before when I made a remark after writing down the Kuznetsov formula. The cutoff. So G. Oh yeah. Thank you. So I'll do this and I'll write G, M, N, C. Okay, because that's determining the length of the sum. Okay, so more generally, there was this story of the Kuznetsov formula that I've written at the top of the board is just at the Poincare series at infinity, the Fourier expansion at infinity. But more generally, we're going to work with other cusps, more generally using other cusps other than infinity. We can actually handle sums of the following kind. So sum over C, sum over M, sum over M. Maybe I'll say C. So I'll let Q and R be relatively prime integers, and I'm only going to sum over the C's, which are relatively prime. to R, and then here I'm going to have a Kloosterman sum with M R inverse plus or minus N C Q. Okay, and then this is also going to be less than something nice. So, okay, it's ugly to write down, but a strong bound, I'll say. And if you want to look at exactly what you get, okay, I refer you to the paper of Decomposition and Vaniach. But these sort of more general things turn out to be pretty useful in a lot of contexts. So, okay, so I don't know. I have about, see what kind of sketch I can give of this. So I'm going to be following, I guess, the paper of Fouvry and Vaniach. So we want to, of course, study the following thing. So Q and A being relatively prime. And then we're going to study the sums of the von Mangoat function. So the first step is to use some combinatorial decomposition of the von Mangoat function. So this is, I guess, known as the Heath-Brown identity. Which seems to be the most flexible version of one of these combinatorial identities, and it's certainly the one that is most useful for this problem. So let's see, I'm going to let Z be at least 2. J is going to be a natural number, and then also I'm going to say that 2Z to the J is strictly bigger than N. Okay, and then I have the following sort of decomposition. So there's going to be many parameters here. So it's M1 product up to Mj, strictly less than Z, and then a product of Mobius functions. And then a sum over a bunch of n variables constrained by the product of the m variables up to j, and one product of n variables up to nj log of n1. Okay, this allows us to kind of get rid of the primes from the story. So if I apply this Heath-Brown identity to the quantity that I want to estimate here, and I also put in a partition of unity to localize all the variables, the sums I have to deal with are of the following shape. So I'm going to let capital M1 up to capital M J. I should say we're going to use Heath-Brown's identity with J equal to 4. Okay, so M capital letters are going to denote dyadic ranges of sizes for each of these variables. Okay, and so what we're going to need to do is need to handle the following sums. So I'm going to sum over the moduli Q A lambda of Q. And then I have the mi variables in a dyadic range about size mi, and then the ni variables in a dyadic range about size ni, and always constrained so that m1 up to mj, n1 up to nj is equal to n. And I have some Mobius functions. Okay, times. So the indicator function of the arithmetic progression. Okay, we'll say need to handle this. Okay, so you can write out a decomposition like this plus a admissible error. Okay, so I dropped the log, and oh, here, this should have been equal to n. I dropped the log, and I dropped the condition here, but you can do this up to an admissible error. Okay, and so then the game is to try to arrange these sets of parameters, these sizes for the different variables, m1 up through mj and n1 up through nj, and pick a kind of arrange them into two pieces. Okay, so we're going to take a partition into two sets. To get bilinear forms. So the kind of bilinear forms that one gets and one kind of ends up having to treat. I'll write down next. So maybe I'll let alpha, beta, gamma, delta sequences all bounded by the k-divisor function, and also such that just the last one of them, such that delta is well distributed in residue classes. So this means it has a Siegel-Wolfus theorem for it. Okay. So i.e. you have something like this. Maybe here n is about size n on both sums, less than, n over log n to an arbitrary power a. Okay, and then the sort of sums that we're going to arrange these bigger messes into look like this. So it's going to have m, n, q, and r. So will be a sum like this. Q goes up to q, alpha, qr goes up to r, beta r, gamma m, m size m, and then the delta is the thing in the middle. Here it's m times n is okay, so the goal is to show that these have some cancellation in them. So maybe it's m, n is about size x. So the goal is for mn running up to x, q kind of staying away from the extreme. And then I guess r, maybe I can always assume it's like bounded by like m to the 1/2. Something like this. So if I can prove such an estimate, what it suffices to do is kind of give a combinatorial rearrangement of all these different parameters into two disjoint sets, which are going to become the m and the n over here. But it's sort of crucial in combinatorial decomposition of these buckets m1, mj, n1 up to nj, that the q and the r depend on m and n, right? So for every different choice of decomposition of these different ranges, I want to be able to pick q and r adapted to exactly that size of m and n. And it's here that one uses the well-factorability of the lambda. Okay, so here we need lambda is well factorable. Okay, I'll just kind of give maybe one or two more lines here just to give you an idea, hopefully, where the Kloosterman sums come from. So the first step in sort of achieving this goal is, well, what we're going to do is we're going to use Cauchy-Schwarz to smooth two of the variables. So I'm going to smooth the gamma variable and the alpha variable. So smooth approximations to intervals. And so then I have the absolute value squared of this gets bounded by qm, maybe log x to some power times something d. So d is going to be a sum like this. And then I'm going to have some betas in the middle. R is about size R. And here it's going to be mn, n is about size n. And here n is about size n squared. Okay, so then I square out and I get something like w minus 2v plus u. And then by expanding this square, each of w, 2v, and u is going to have a main term that cancels with each other. And then I'm going to get like two r variables and two n variables. So w is going to be the hardest. and we're going to end up with 4 variables. R1, N1, R2, N2. And they're each going to have some congruence conditions like this. And this will actually, OK, there's some residue classes, and I can expand them using Poisson summation. And this is going to give actually Kloosterman sums of modulus R1N2. So there's this kind of interesting thing that happens. Sorry, I'm out of time. Where after you expand the square, I get these 4 variables, R1, N1, R2, N2. And the R and N variables from the 2 factors in the square kind of get crossed to produce these Kloosterman sums after you resolve everything with additive characters in Poisson summation. So sorry I ran out of time, but I'll stop there. Yeah.
I guess, do you have anything to add philosophically about why that helps?
So it seems it's pretty important in this argument that I have a lot of flexibility in all the different ranges that I can take the M and the N. So there's kind of a lot of other little bells and whistles that I brushed under the rug here. But among them is that for certain ranges of the M and N, I can treat the delta with this Siegel-Wolfes condition. And in other ranges, I can assume delta looks just like the indicator function of an interval. OK, so this goes into this kind of like combinatorial arrangement. Sometimes I can take the delta to be looking like the smooth variables, and sometimes I can take the delta to be looking like the Mobius functions. OK, and then I can actually get stronger results, meaning for like better ranges of Q and R, in the case where I have a smooth variable all the way on the inside of these bilinear sums than if I have the Mobius function all the way on the inside. And it's kind of like you can just eke out and use enough of that extra advantage to finish the problem. So I would say like here, one of the advantages is all of a sudden you go from having something like the lambda function to having this great flexibility in all these different parameters that you can arrange and play different games with and try to win a little bit by either choosing a smooth or non-smooth variable when it's advantageous. So that's maybe in this context, that would never be possible if I tried to do something with the lambda function directly. And for the more general picture, well, I don't have that much to say. Yeah.
Yes. So I have one question. So you recovered the Selberg gap, exactly the Selberg gap.
Mm-hmm.
Now there are several relatively soft or conceptual methods, however you want to put it, that recover a gap that is positive but it's not Selberg's.
Mm-hmm.
Do you recover the same gap as Selberg, you think, by chance, or is there really a deep reason why you recover exactly that gap and not another?
Isn't this how Selberg proved his result?
That would be the trivial
Yeah.
reason.
I think that's the, I think.
Because when Selberg proved it, the Kuznetsov formula was not available.
Yeah, so in fact.
He had a different
But
decomposition.
he used the Selberg trace formula.
Uh-huh.
And at least he used Poincaré series.
Yeah.
And so morally, he used exactly that proof.
So is that written down in like the discontinuous groups paper, or because he sort of mentions it in the paper on estimation of Fourier coefficients, but he doesn't really like give a full proof of that. So did he write it down, or did he just kind of claim it and?
It's the kind of proof that you would expect.
Okay, yeah, I see. So.
So deep down it's the same proof. I mean,
Yes, it's the exact same.
Yeah.
All right. But it's a different proof problem.
I mean.
So he uses, I mean, not really, he uses Poincaré series.
Yeah.
So he just doesn't write down the Kuznetsov formula, but he has principle the ingredients available.
The paper is about Poincaré series, and then he has this result, and he doesn't give all the details. But so it's clear he's kind of thinking about this. He's not really thinking about the general version of the trace formula. But he doesn't really give all the details.
Are you asking why the Selberg gap matches the gap coming from Gelbart-Jacquet, which comes from symmetric square? Was it your question about the coincidence?
I had a less sophisticated question. My question was really why the Selberg spectral lab is saying that we were recovering here, but your question is more interesting, so I would like to hear your answer.
I don't know.
But Gelbart-Jacquet do like just a little better, right? They get strictly bigger than 3/16. Is that right?
No.
That's another paper I'm thinking of.
You get 3/16.
Okay.
When you have your opening Cernac, then you can push a bit further.
Yeah.
Or,
And then
Serre,
finally.
but if you do blindly, just functoriality gives you the 1/4.
Yeah. And then if you have the symmetric fourth and fifth, that's the Kim-Sarnak. So.
But then it means you have been able to detect cancellation in your Kloosterman sums
Yeah.
in spirit.
Yeah.
Adam?
Yeah, so I just have a remark rather than a question. So in the BFI theorem that you wrote down, it was asked whether it's permissible to have absolute values
Mm-hmm.
on the inside, and as you said, it's not known how to do that. But what you really need there is you need some well factorability somewhere.
Mm-hmm.
So if instead of having some of the primes on the inside, so you're looking at primes of progressions, you had an arithmetic sequence that were itself well factorable,
Mm-hmm.
then you can have absolute values. So there's a nice result of Petrow, which was mentioned in Daniel Thurley's talk, but he didn't explain exactly what it said. So there he looks at the distribution of smooth numbers and progressions. Because smooth numbers are themselves well factorable, unlike the primes, then you can have absolute values. You don't need the well factorable lambda.
Uh-huh.
You can go up to x to the 4/7.
Okay. Thank you.